Welcome back. Today we've got an absolute powerhouse of an explainer lined up for you. We're going to completely decode Section 5 of the TEMA mechanical standards. Think of this as a complete, zero-omission walkthrough of the rules that govern Class R, Class C, and Class B heat exchangers. We're going to look at the exact, rigorous parameters that dictate how these massive, incredibly complex pieces of industrial equipment are actually designed, tested, and protected in the real world. So if you've ever wanted to truly understand the literal rulebook of heat exchanger design, you are in exactly the right place. Let's get into it. Here is our blueprint for today. We're going to hit scope, classes, and codes, then jump right into pressure and testing, followed by metal temperatures, corrosion allowances, service limitations, and finally, we'll wrap up with anodes. All right, starting us off, Section 1, Scope, Classes, and Codes. So the math setting the boundaries here is incredibly precise. The TEMA mechanical standards apply to shell and tube heat exchangers that fit within some very specific criteria under RCB-111. We're talking about a maximum inside diameter of 100 inches and a design pressure cap of 3,000 psi. To put that into perspective, 3,000 psi is roughly the pressure of a fully loaded scuba tank. There's also a limit where the product of the nominal diameter and design pressure can't exceed 100,000. Now, you might be wondering, why these specific numbers? Well, the intent is actually to purposefully cap the sheer physical thickness of the metal used. It keeps the shell wall thickness to about 3 inches and stud diameters to roughly 4 inches. Though, interestingly enough, the code does mention that these standards can still be applied to units exceeding these parameters if it's really needed. Now, TEMA cleanly slices these exchangers into 3 distinct classes. Class R is your heavy-duty category. This is for generally severe requirements, stuff like petroleum and heavy processing. Class C is for your moderate requirements, so think commercial and general process applications. And then you have Class B, which is explicitly for chemical process service, and that one strictly requires the application of the code symbol. But across the board, under RCB.113, every single one of these vessels must comply with the overarching ASME Boiler and Pressure Vessel Code, Section 8, Division 1. State and local codes apply too, of course, but the purchaser actually has to specify the plant location to the manufacturer to ensure total legal compliance. Okay, this next part is absolutely crucial. It's how the standard legally defines its materials. Under RCB 1.14, carbon steel specifically means any steel or low alloy that falls within Part UCS of the code. Literally anything else except cast iron is just considered an alloy unless it's otherwise named. But here's the real kicker, the biggest takeaway here. The materials of construction, right down to the gaskets, must be specified by the purchaser. The manufacturer assumes zero, and I mean absolutely zero responsibility for the deterioration of parts for any reason. So the legal and financial responsibility for picking the right metal for the right chemical environment, that falls entirely on the buyer's shoulders. Moving right along to Section 2, Pressure and Testing Rules. Here is a super short but literally foundational rule under RCB 1.21. Design pressures for the shell side and the tube side shall be specified separately by the purchaser. You absolutely cannot just treat the heat exchanger as one big single pressure zone. They are completely separate engineering variables and they have to be calculated and declared individually. So, how do we actually prove these vessels can handle that stress? They face the ultimate proving ground, the RCB 1.31 standard test. First up, welded joints have to be cleaned sufficiently so they can actually be inspected properly. Next, the unit is hydrostatically tested with water for a minimum of 30 straight minutes. And just like we saw with the design parameters, the shell side and the tube side are tested totally separately. This is to isolate any potential leaks right at the tube joints. Oh, and if the tube side design pressure happens to be higher than the shell side, the tube bundle actually has to be tested completely outside of the shell, assuming the physical construction even allows for that. But hey, what if water just isn't an option for your specific setup? TEMA does allow for alternative testing methods, but they come with some really strict conditions attached. Under Code 1.311, you can use other liquids, but only if both the purchaser and manufacturer agree on it. Now, if liquid literally cannot be tolerated at all, Code 1.32 allows for a pneumatic test using air or gas at room temp. But listen, the standard issues a grave safety warning here. Air or gas is officially recognized as hazardous when used as a pressure testing medium, so it's serious business. Finally, under 1.33, you've got a supplementary air test, but that one must be preceded by the standard hydrostatic water test, and the pressure absolutely cannot exceed the hydrostatic limit. Okay, let's turn up the heat. Section 3, Metal Temperature Specifications. When it comes to the absolute baseline temperature limits for the different metals used in pressure parts, TEMA actually keeps things incredibly straightforward. Under RCB 1.41, they simply and honestly very smartly defer directly to the overarching limits prescribed by the ASME code. It's a great move because it creates total universality and prevents any kind of contradictory guidelines from messing up the design process. Now, TEMA creates this brilliant sort of fork in the road for determining design temperature under RCB 1.42. It all boils down to where a part is physically located inside the unit. For parts that are not in contact with both fluids, that's governed by 1.421, the purchaser specifies the design temperatures separately for the shell and tube sides, and then the code just provides the allowable stress limits. Simple enough, right? But for parts trapped between both fluids, like the tubes themselves under 1.422, the design metal temperature has to be based on the operating temperatures of both the shell side and tube side fluids. And here's a really cool detail. If a purchaser specifies a design metal temp that's lower than the highest of those two fluid temperatures, that specific lower design temp literally has to be permanently stamped right onto the manufacturer's nameplate. We actually see a really similar logic applied to calculating the mean metal temperature, which you need to establish metal properties under operating conditions. Under 1431, if the part is only touching one fluid, you just calculate the mean temperature based strictly on that one fluid. Easy. But under 1432, if the part is touching both fluids, the math gets way more complex. You have to calculate the mean temperature based on both fluids, plus you've got to factor in the heat transfer coefficients of those fluids and the relative heat transfer area of the parts contacted by them. It's this highly precise balancing act, kind of like an intricate thermal tug-of-war happening between the two fluids. All right, Section 4, Standard Corrosion Allowances. Let's talk about the mandatory physical buffers against wear and tear. Sweeping through the detailed RCB 1.51 specs for carbon steel, look at the baseline difference right at the top. Heavy-duty Class R pressure parts require a corrosion allowance of 1/8 of an inch, or 3.2 millimeters. Moderate Class C and B parts, they only require half of that, just 1/16 of an inch. Beyond that baseline, the code gets super specific. For internal floating head covers, the allowance is applied to all wetted surfaces, including the outside flange, but skipping the gasket seating surfaces. For grooved tube sheets and external flat covers, the actual depth of the gasketed groove is considered available for that corrosion allowance. And for end flanges, you only apply the allowance to the inside diameter where it's actually exposed to the fluids. But wait, not every single part needs this extra padding. There are some really specific exceptions baked in. Under RCB 1.516, you're not required to have a corrosion allowance for non-pressure parts, so things like tie rods, spacers, baffles, and support plates are exempt. Same goes for tubes, bolting, and floating head backing devices under RCB 1.517. Pass partition plates and welded-in long baffles also exempt under RCB 1.518. And, crucially, all alloy parts, which, remember, means anything not defined as carbon steel or cast iron, do not require a standard corrosion allowance under the RCB 1.52 rule. Now, if we swap over to cast iron, specifically under Section 1.53, we see the exact same fractional contrast that we just saw with carbon steel. Cast iron pressure parts for those severe Class R applications must have a 1/8 inch allowance under R 1.53. For Class C and B, it drops right down to a 1/16 inch allowance. It's just a perfect illustration of how TEMA purposefully scales structural durability to directly match the intended severity of the application. Moving in to Section 5, Service Limitations. This is where the rules urgently shift from how to build it to where you absolutely cannot use it. The real-world limitation placed on cast iron is intense. For Class R and B exchangers under RB 1.61, cast iron is strictly limited to water service only, and pressures cannot exceed 150 psi. You literally cannot use it for anything else. Now, for Class C exchangers under C 1.61, that 150 psi limit stays, but the code explicitly states that cast iron shall not be used for lethal or flammable fluids at any pressure whatsoever. It's a complete absolute ban based entirely on safety. Another really serious safety-driven ban involves external packed joints. Under RCB.1.62, the rule is crystal clear. They shall not be used when the purchaser specifies that the fluid in contact with the joint is lethal or flammable. And again, notice the theme here. The safety reliance completely depends on the purchaser correctly identifying and declaring the dangerous nature of their operating fluids up front. And finally, let's hit Section 6.
Guidelines for anodes.
Anodes. They're sacrificial metals used to control corrosion. But according to the RCB 1.7 standards, selecting and placing them is actually not the responsibility of the heat exchanger manufacturer. Not at all. If a purchaser wants anodes included, they have to hand over 5 non-negotiable pieces of information. They have to specify the method of attachment, the quantity required, the exact size and manufacturer of those anodes, the material itself, and they even have to provide a sketch detailing the exact locations and spacing. The purchaser holds all the engineering responsibility on this one. And the standard just totally punctuates this division of responsibility with a direct, unequivocal quote. Even if the manufacturer installs the anodes for a customer, the rulebook says the manufacturer is not responsible for the suitability of the anodes for the service it is installed in, the life of the anodes, the corrosion protection provided by the anode, or any subsequent damage to the heat exchanger attributed to the anode, the method of anode installation, or the installed location. It is a complete legal and technical absolution of the manufacturer regarding how well those anodes actually perform. Wow, we've covered a massive amount of incredibly precise ground today, haven't we? From maximum inside diameters and 30-minute hydrostatic stress tests to exactly 1/16 of an inch of mandatory corrosion buffering, all the way to the rigid legal boundaries for anode placement. It leaves us with a pretty provocative thought to chew on. When every fraction of an inch and every degree of heat is so deeply legislated by standards like TEMA, how do these strict, shared responsibilities between the buyer and the builder shape the true future of industrial engineering? Thank you so much for exploring this explainer with me today, and keep questioning how the rules shape our world.